this talk, and I thank you, the organizers, for giving me this opportunity. And I would like to tell how massive rotating neutron stars can be, and talk about our results in this field. Okay, from the beginning. We are interested mostly in the maximum mass of rotating neutron stars, but from the beginning. For the static case, the maximum mass of neutron star is most described by Thorman-Oppenheimer-Volkoff equations, and only depends on the equation of state and assumed central density. For rigid rotation, we also have the limitation of the angular velocity when the configurations reaches the mass shed limit, and mass of such configuration rotating at mass shed limit could be from even up to 20% greater for a neutron star, or even greater by 44% for quark stars compared to the non-rotating case. And here's some picture that here by this black line are plotted configurations, static configurations, and this maximum mass. And here by this red dashed line are marked configurations rotating at their maximum angular velocity, and this mass could be, the maximum mass of such configurations could be much higher than for non-rotating case. Then we can try to investigate the influence of differential rotation. But firstly, when the differential rotation appears in neutron or strange stars. After a collapse of a massive star and observed supernova explosion, or as a neutron star binary merger, and after such events the neutron or quark stars could rotate differentially. And from some previous calculations, we know that the differential rotation is very efficient in increasing of maximum mass of these compact objects. For example, it could be by Baumgartner, Shapiro, Shibata showed that it could be greater by 60%. And in our calculations, we assume this very simple differential rotation law, introduced by Kucaba and all. And what is very important, we have introduced some factor A tilde, which describes the degree of differential rotation. And for A equals 0, we have rigid rotation, and when A tilde increases, we have a greater degree of differential rotation. And here we have the angular velocity profiles of examples of such profiles for two cases. Here is A tilde about 0.4, and here is about 1.0, so you can see how it looks like. And we also perform calculations with assume the polytropic equation of state. Okay. How we perform our calculation? We start with the spherical configurations, and we increase the rotation of such an object, and it causes the flattening of the star. And at some point we achieve a configuration with the maximum mass. And for calculation performed by Baumgartner, they show that this increase of maximum mass can be quite high, but there are some other these dotted points are the results obtained by Baumgartner, Shapiro, and Shibata, and these solid lines are results obtained by our work, and we can see that there is some difference between these two results, and where this difference comes from. Mostly and they were limited by some numerical limitations that couldn't allow don't allow them to obtain some part of configurations. Why? Because when we start with this error ratio, with this polar radius to equatorial radius ratio, when we start with this spherical symmetric star and increase its angular velocity, we cause the decreasing of such a value. And we may see that when we increase this angular velocity, we obtain much higher massive objects. But we have noticed that we may divide these configurations in some types, and here are plotted two types of such configurations. Type we call them type A, marked by these solid lines, and type C, plotted by these dashed lines at end. Type A exists for a smaller degree of differential rotation, and type C exists only above some critical value of degree of differential rotation. And for type A, we have the maximum mass very close to the mass shed limit configuration. But in the case of type C, the maximum mass is close to this error ratio, close to 0, which corresponds to toroidal shape case. And how these configurations looks like. For this type A, it's something like there are configurations with very smaller degree of differential rotation. Here's example which rotates close to the mass shed limit with this A tilde close equals 0.3. But also we can have the configuration of type C, which rotates with this A tilde close equals 1.0, and this configuration is close to the configuration with the maximum mass. I haven't mentioned it. The vertical line of symmetry is the rotation axis of such an object. So we can imagine this is some oblate and flattened ellipsoidal shape, and this is some close to toroidal shape configuration. And what we have also noticed, we have additional, besides these two types, we have additional two types of configurations. We call them type B and type D of configurations. First, a very important thing, they exist only due to differential rotation. We cannot obtain them with starting from a spherical object and increase its angular velocity. Also, they exist at some limited, for some limited values of degree of differential rotation, and for smaller values of mentioned error ratio parameter. Okay, and when here we have the areas of existence of such configurations. Type A exists with for every degree of differential rotation greater than 0 and below some critical value plotted by this thick black line. But above some threshold value, we may have coexistence of type A and type B of configurations. They may have the same degree of differential rotation, but have appear in different regions of the error ratio regime. And above this critical value of a degree of differential rotation, we have type C, and here some small area when type C and type B coexist together. And this existence of such types strongly depends on the maximum density inside the object. Okay. And here we have the comparison of maximum mass for type A and type B of configurations. The black line is the mass for static limit configurations, and for type A we have this solid blue line, and for type B we have this solid red line. We may see that the degree of differential rotation is the same for these two types, but the type B could be much more massive than type A. And here is some summary for one of the equation of the state. Here we have depends of the increase of maximum mass as a function of the degree of differential rotation. And for type A we have the increasing function of maximum mass with the increasing degree of differential rotation. But for type B and type C we have opposite case when the maximum mass is decreasing function with increasing degree of differential rotation. And what is more important, this newly found type B is could be much more massive than this non-rotating or rigidly rotating configuration. And going to some summary, performing the calculations by our code, we have found 4 types of solutions. 2 of them exist for modest degree of differential rotation, and for this ratio less than, let's say, 0.3. And these 2 types were not considered in previous works. Differential rotation may significantly increase the maximum mass of neutron star, and may temporarily stabilize a remnant of a binary merger. The maximum mass of rotating neutron star strongly depends on the both type and degree of differential rotation. Was not considered before. More. The maximum mass is increasing function of 80 degree of differential rotation for type A and decreasing for types B and C. And the highest increase of mass is obtained for this newly found type of neutron stars. And such an object could be very good sources of gravitational waves, and when we observe them in gravitational waves detectors, we can may be able to distinguish the outcome of the neutron star binary mergers. And what we want to do in future, and part of this is now we're working on. We are trying to introduce realistic equations of state to our code. Then we will try to test the stability of obtained configurations. We will consider them as sources of gravitational waves, and maybe try some different differential rotation law. And for more about differential rotating neutron and strange stars, I encourage you to come at the talks on Monday. Thank you very much.